cloaking will be a part of it. And this talk is going to be expository. There will be several deep theorems, but none of them will be proved. And but on the other hand, I will pepper you with a lot of open problems. And as you will see, it has close connections to the geometric version of Calderon problem, which I will state in just in probably the next slide. And I have 2 slides on cloaking and 2 images on cloaking, and that's courtesy Professor Matti Lasses, who could not come due to professional reasons. So what is the geometric Calderon problem? So I consider, so far Professor Rakesh talked about the isotropic case, where the sigma here, instead of it being a matrix, it was a sigma times the identity, right? But it's natural to consider the case when instead of sigma times the isotropic case, you have the non-isotropic case, where we replace this by a matrix. And then you can ask the same problem. You consider the following boundary value problem. So this is similar to what you saw in Professor Rakesh's lectures. And then you have lambda sigma, which is the Dirichlet. So this is the Dirichlet data. And then you have the Nyman measurements, so the Nyman data. So you define the Dirichlet and Nyman map. And then you ask the question, does lambda sigma determine sigma? So as Professor Rakesh mentioned in his lectures, if you consider the sigma to be the identity, then sigma times, that is sigma of x times the identity, then we saw that this Dirichlet and Nyman map does indeed determine sigma uniquely. And he also mentioned that
sigma 1 and sigma 2 in the same form.
Say that again.
See, that uniquely determined provided if you have sigma 1 and sigma 2 given by sigma 1 times identity and sigma 2 times identity.
Yes.
Now, if one is, can you get a diffeomorphism which gives one to them? So one of them is sigma times identity, another is not in the sigma times identity.
And with the same boundary measurements.
Of course.
No, you can't.
No, that's the problem. Even in the I'm asking in the simplest case.
I don't know the answer. So for the if you have so if you consider one to be isotropic and the other to be non-isotropic, yeah, I don't know the answer offhand.
Even in the diagonal form.
You mean sigma 1, sigma 2, sigma n? So the conjecture would be, the natural conjecture would be that one is you can get through a diffeomorphism to the other case. I think that is the most likely. I don't know whether it's proved, but I think that would be the natural conjecture. Okay, so then we also saw in Professor Rakesh's lectures that if you have a diffeomorphism and which fixes the boundary, which means that f restricted to d omega, which I'm assuming is going to be smooth and all the nice geometries, then the Dirichlet-Nyman map for f star sigma, which I have defined here, so you can view this as the push forward of the matrix sigma. So then you have that lambda f star sigma is the same as lambda sigma. Right. So this is all nothing new that we have seen. So this was what was done already.
The diagonal case is equivalent to this at the single function case, because then you can isolate.
You mean sigma 1, sigma 2?
Right, and then just u1, so just the same different problem that you're comparing with the single one. So that's the decoupled as a single case.
So, yeah, so it may be the same as the scale. Yeah, right. Is that right? Is it the same as the scalar case? But anyway, I don't want to spend time here. So then what we do is we consider the geometric version of this problem, and I call it the geometric Calderon problem. It's not something that is I just coined it just for here. So you consider a smooth compact Riemannian manifold with smooth boundary. I'm going to assume it is which has this nice geometry, and then we consider the Laplace-Beltrami operator with Dirichlet data. So that's here. U restricted to dm is equal to f, and this is the Laplace-Beltrami operator. And you can ask the same problem. So you have the Dirichlet-Neumann map. So you consider with the Dirichlet data, you consider the Neumann data. So this is the Neumann data. And then you can ask the same question: does this determine G, where G replaces sigma? And it's a trivial thing. If you show that it doesn't determine in that case, it also doesn't determine in this case. In fact, there is a relation between sigma and G, and this is only true in n greater than or equal to 3 dimensions. It's not true in the case of 2 dimensions. And there will be some, probably in the next slide you will see that there is something more to it. So if n is greater than or equal to 3, then you can go back between the Calderon problem that I just mentioned for the non-isotropic case with the geometric Calderon problem that I mentioned here. But you can go back between these two. It's these two are equivalent. Okay. So as I just said, so the question is, does lambda G determine G? The answer is clearly no. And again, the same story. If you have a diffeomorphism that's fixing the boundary, then the Dirichlet-Neumann, the Dirichlet operator corresponding to the pullback of the metric G is the same as the Dirichlet-Neumann map corresponding to G. Okay. Now, so this leads to the natural conjecture. So the conjecture is that you have a smooth compact Riemannian manifold with boundary, and the dimension here n greater than or equal to 3. Then suppose you have G and G tilde. Suppose they are smooth Riemannian metrics with the Dirichlet-Neumann maps are the same. Then does it imply that there exists a diffeomorphism that's identity on the boundary, or in other words, fixing the boundary such that you can get this G through a pullback of the diffeomorphism of this metric G tilde. So this is the conjecture. And I should also tell you what happens in the 2-dimensional case. 1-dimensional case, this is not enough information, so 1-dimensional case we will discard. So in the 2-dimensional case, there is something called this conformal invariance, and this is also was seen in the previous slide, where you could go back between the Calderon problem for the non-isotropic case with the geometric Calderon problem. The transformation was valid only in 3 dimensions and higher. And there is also this conformal invariance here. So if you consider the same problem, the same as before, that is, you have a compact Riemannian manifold, and then you have the Dirichlet-Neumann maps corresponding to 2 different metrics, then does it imply that there exists a diffeomorphism and a smooth positive function phi that's identity on dm, such that G is, so it's not just phi star G tilde, the pullback of G tilde, but you can also, because of this conformal invariance, you can also have this phi there. Phi that's identity on the boundary and it's positive. So if you want, you can replace this by e to the phi, as is usually done in Riemannian geometry. So, and this is due to the conformal invariance of the Dirichlet problem that's valid only in 2 dimensions. So these are conjectures that are, as we speak, still open, but there are some partial results, and there are also actually there are several partial results, but this is also a motivation towards cloaking, and I will motivate that in the next few slides. So let me tell you what are the known results. So the known results is, so simply if you consider the metrics, so the G and G tilde to be real analytic. So you have M as a compact, so you need the simply connectedness, and then you have a real analytic N manifold and with real analytic boundary, and then you also require that G and G tilde be real analytic metrics, and if you have lambda G is equal to lambda G tilde, then you require these this is a condition that was present in this paper by Lee and Ullman in 1989. So this appeared in CPAM, but this can be removed, as we will see in the next slide. But forget about this. But suppose you have real analytic metrics, then there exists a real analytic diffeomorphism such that G and G tilde are related by that real analytic diffeomorphism fixing the boundary. And the proof, so let me just give you a flavor of where the real analyticity is required.
So the real analytic metrics on M, is that what you meant, right? The start of the...
Oh yeah, this should be M, not DM. This one, right? Yeah, this should be M, sorry. This is DM, this is M. So I can tell you where analyticity is required. You need analytic continuation. So the proof goes as follows. From this lambda G, you can determine the Taylor series of G at the boundary. Actually, you can do a little bit better. You can actually determine the Taylor series of G in a small tubular neighborhood of the boundary. And once you have that, then you want to real analytically continue. So that's where the simply connectedness is required. Actually, simply connectedness is a strong assumption. You require that pi 1 of M dm is the trivial is 0. So, but anyway, we will assume simply connected. So if this is true, then you can analytically continue, and that produces this real analytic diffeomorphism. And so this was done for the 3 dimensions and higher. And Lassus and Ullman in 2001 substantially strengthened this, and actually they also proved this for 2 dimensions. And so in this case the assumption as before, so M is either a connected Riemann surface for 2 dimensions, and if n is greater than or equal to 3, it's a connected real analytic Riemann manifold with real analytic boundary DM. And if you assume that, so by real analytic Riemann manifold, I mean M is real analytic, G is also real analytic. So this is required for 3 dimensions and higher, because there is analytic continuation involved even here. But for 2 dimensions, that's not the case. So 2 dimensions is important that it is only C infinity. Then if you have n is equal to 2, then you have that lambda G actually determines the conformal class of the metric G. So based on the conformal invariance, this is the best that you can achieve in 2 dimensions. And in 3 dimensions and higher, you can determine, so from lambda G, you can determine G up to the natural obstruction. By natural obstruction, I mean the G tilde that you determine differs from G through the pullback. So G tilde is psi, the pullback of this metric G. And based on the gauge invariance that we saw earlier, this is the best that one can achieve, or with real analyticity, this is the best that one can achieve in 3 dimensions and higher. But the natural question is, if you remove analyticity, is if for n greater than or equal to 3, whether this is still true, that's still an open question. Okay. Now, the fact that you have this obstruction here naturally leads to cloaking. So that's one of the applications of this geometric Calderon problem that I will first go through that. But it also has connections to several inverse problems of geometric nature, and I have at least 4 or 5 in the next slides. And that's what I'll do. And it's a little unfortunate that Marty Lassus could not come. For cloaking, there are 4 main authors, and I'm listing them in alphabetical order. It's Lassus, Greenleaf, Lassus, Kurylev, and Ullman, and I'm not one of them, so I cannot do justice to cloaking. But what I'll do is I will try to emphasize connections to other inverse problems that I'm aware of based on the geometric Calderon problem. Okay, so this is the theorem of Greenleaf, Lassus, and Ullman, and this came in 2003. And this was the paper that, it depends on it looks like there are two different fields, two different sets of people, but it is true that they came up with this, with the idea of what could, cloaking was not a word used when they actually proved this result. They saw this as a way of showing non-uniqueness of the Calderon problem. And a different set of people came with the idea of cloaking, but they were the ones to come up with this idea first. So what you have is you consider the same a metric, and what you can do is you can consider a diffeomorphism. So this omega, we can assume it's a smooth bounded domain with a smooth boundary, and then you construct a diffeomorphism f from omega, and I will show the diffeomorphism in the next slide. This is taken from this paper, Greenleaf, Lassus and Ullman. So you construct a diffeomorphism from omega minus a point to omega minus a ball in 3 dimensions and higher, and that satisfies these conditions. So let's not worry about these right now. And what we have is, so then you consider G tilde, which is the push forward of G. So that gives you a metric on omega slash d bar. D bar is a small ball, and that is what gives us cloaking. And then what you do is you extend this G tilde into D such that it is positive definite. So this G tilde is not going to be positive definite everywhere. It's only going to be positive semi-definite. But at least inside D, you want it to be positive definite. So if that is the case, then if you consider the corresponding conductivities, which if you recall, it was in terms of this some power 1 over n minus 2. This one. So this is how you relate the conductivity to the metric. And remember that this is in 3 dimensions and higher. So then if you consider the corresponding conductivities, then the Dirichlet and Neumann maps are the same. And what is true here, and this is what gives the or leads to the idea of cloaking, is that the sigma hat, the continuation of G tilde inside D, and correspondingly the conductivities, they can be changed arbitrarily inside D without changing the boundary measurements. Because see, all that this theorem proves, or this theorem what it states is that you can continue this G tilde arbitrarily inside into D. The only condition is that it should be positive definite. But if that's the case, then the corresponding measurements at the boundary are the same. So then, so that's his remark. And
why is arbitrary in this case? Why is arbitrary point or?
Why is any point? It doesn't matter.
Maybe in case of 2 dimensions, the simply connected will be lost if I choose.
Yeah, but this is not valid in 2 dimensions. This is only invalid in 3 dimensions and higher.
Let's say maybe this theorem is not working in 2 dimensions.
Yeah. So you consider B of the ball of 0, 2, the ball centered at 0 of radius 2 contained in R3, and this is a diffeomorphism that takes this omega, which is B of 0, 2 minus the origin, to omega minus the ball of radius 1. So this is D contained in B. D is equal to B of 0, 1. So this the ball of radius 1 centered at 0. And then if you consider the homogeneous conductivity, gamma is equal to 1, and then you consider based on the push forward of this, you consider the conductivity sigma, and then you continue it inside D such that it is C infinity smooth and D. This provides, so this is an example of this theorem, or the F in this theorem. Now, Professor Marty Lassus was kind enough to provide to give 2 movies to illustrate cloaking, so let me do that. So this is the case corresponding to if you consider gamma is equal to 1. So this is the current patterns. Maybe it went too quickly, so let me just. And and this is a case in which you have a cloaked shell. So
Pause there.
pause, yeah. And this is a case in which you have the cloaked shell. So whatever measurements that you make at the boundary, this what you can hide anything here. It's not going to be visible to outside measurements. And the previous paper is what began all this, and there are several. They have several works in this direction, and if you are interested, I can provide references after this. Okay. Yeah, so 2 movies to illustrate cloaking, and these are due to Professor Marty Lassus. Okay, so now that we have the geometric Calderon problem, I will illustrate its connections to several other problems. One of them is the still unresolved boundary rigidity problem. So what is boundary rigidity problem? So this is so you consider a compact Riemannian manifold, and I'll put additional conditions in the manifold later. And the question asks, the boundary rigidity question asks, if you know the boundary distance function, that is, you take any 2 points in the boundary and all that you know is the distance dg corresponding to these 2 points on the boundary, is there enough information to actually reconstruct G inside? Okay, so you have a manifold, and then you take any point. It can be any 2 points, and then, well, uniqueness is guaranteed. Uniqueness is not guaranteed, but suppose you have a unique geodesic connecting these 2 points, then you know dg of x comma y. From this, can you determine G? And there is a surprising connection to Calderon problem, the geometric Calderon problem, at least in 2 dimensions, as you will see. So, as before, that is, as in the case of the geometric Calderon problem, there is a natural obstruction. That is, if you consider any diffeomorphism psi such that it is identity on the boundary, and then you consider 2 metrics, G and G tilde, which is the pullback of G, then they have the same boundary distance functions. So the dg is, so from this you cannot determine G uniquely, right? So this is a trivial example where you cannot determine, so which shows that you cannot determine G uniquely. Then the question is, can you determine G up to this natural obstruction? Okay, and again, it's not true that you can determine G uniquely. For instance, you can have manifolds in which this is a boundary distance function, right? So it tries to take the shortest travel time. So suppose you have, say, some interior point in which the metric is really high, then all geodesics is going to try to avoid the place where there is high, it has to work harder to go scale that peak, so it's going to try to avoid it. So if you have some region where no geodesics pass through, then there is no hope for recovering the metric in the neighborhood of that point. So some additional hypothesis is required. So one hypothesis, and I don't know who actually formulated this, probably it was René Michel, is to assume that the metric is simple. By simple I mean, so simple I mean the boundary should be strictly convex, and so this is the X map. So this is, you consider any point on the tangent space, right? So any vector on the tangent space, and then you flow for a time 1. So that is the X map, and it should be a diffeomorphism. So roughly speaking, what this means is that between any 2 points in the manifold, not just at the boundary, but any 2 points in the manifold, there should be a unique length minimizing geodesic connecting these 2 points. So this is what we assume, this is what we mean by a metric being simple. And so then the conjecture is that if you assume two compact simple Riemannian manifolds with boundary, and if you have dg1, which is the boundary distance function corresponding to the first metric, and is equal to dg2, which is the boundary distance function corresponding to the second metric, then the conjecture is that there exists a diffeomorphism psi from M to M, such that these two are related through this way. Okay, and this conjecture is still open in 3 dimensions and higher. In 2 dimension, it is a famous paper by Pestov and Ullmann that this problem is that this is actually true, that there exists a diffeomorphism psi from M to M such that G1 is equal to psi star G2 in the case of 2 dimensions. And you will see that there is a connection to the geometric Calderon problem. So there is a connection, and what is that connection? So the connection is this, again, this result. So the same setup as in this conjecture. So you have compact simple Riemannian manifolds with boundary, with the boundary distance functions being the same. Then in 2 dimensions, what they prove is that if dg1 is equal to dg2, then the corresponding Nyman maps are the same, corresponding to the Laplace delta, the geometric Calderon problem. So lambda g1 is equal to lambda g2. Now, why is it that this settles? So all the work in the paper was to prove this result, and this required surprising connections. It contains several surprising results, but this was the main theorem. And once they had this theorem, then previous results show that with this you can determine G up to the natural obstruction. So why is that? Because earlier, recall that in the C infinity metric case, in 2 dimensions, lambda G determines G in the conformal class, right? It doesn't determine up to the psi star G, but it determines in the conformal class. And then there is an earlier result of Mukhametov that says that the conformal factor has to be equal to 1. So once they prove dg1 is, that is, if you have dg1 is equal to dg2, then this conformal factor has to be 1. So this is a result of Mukhametov. So once you have dg1 is equal to dg2, with this you can show, you can prove the boundary rigidity problem in 2 dimensions. And as I said, in 3 dimensions and higher, this is an open problem. And the study of this was motivated by travel times of seismic waves. So it was motivated by seismic imaging. Okay, so now what is the conjecture? So, well, maybe boundary rigidity problem is too hard, but maybe we can still try to prove, or we can attempt other problems related to this. So let me state a couple of conjectures. So one is the same as here. Everything as in the previous setup, and what they show is only in the case of 2 dimensions, that if n is equal to 2, then dg1 is equal to dg2 implies lambda g1 is equal to lambda g2. Now you can ask the same question in 3 dimensions and higher. So if dg1 is equal to dg2, that is the boundary distance functions are the same, does it imply that lambda g1 is equal to lambda g2? That is the Nyman, the Dirichlet-Nyman map, are they the same? And in 3 dimensions and higher, it's still an open problem. But actually we can go the other way around, right? So maybe this is too hard. So we can go the other way around. Let's consider n greater than or equal to 2 dimensions and higher. If lambda g1 is equal to lambda g2, does it imply that dg1 is equal to dg2? I believe this is a simpler problem. This is a simpler problem corresponding to the first case, but
There's a lot more information there.
yes, there's a lot more information, and there is actually one more reason, which is in the next slide. So, this is again an open problem. Now, why is it that at least I believe that this can be done a lot quicker, and because this is true in the dynamic Dirichlet-Nyman. In the hyperbolic case, this is true. And so you consider, so this was done by Professor Kurile, so I'm not going to repeat all those things. So you consider the hyperbolic Dirichlet-Nyman map, which is given here. Then, here you only assume that G is C infinity, right? There is no analyticity. You only assume that G is C infinity, and you assume that G is simple. then the boundary control method, which Professor Kurilev talked about, shows that if T here is sufficiently large, then you can determine from lambda G, and I put H for the hyperbolic case, uniquely determines G up to the natural obstruction. That is, it determines G tilde, and this G tilde and G are related by the pullback of the diffeomorphism fixing the boundary. Now, it is a result of Sylvester and Woolman that says that, so here you require that this T to be sufficiently large, right? And, but you take any T here, and then if you consider compact simple Riemannian manifolds with boundary, and if you have the hyperbolic Dirichlet-Neumann maps are the same, then the boundary distance functions are the same. And so this is true in the hyperbolic case. In the elliptic case, it's still an open problem. So this is one connection of the geometric Calderon problem to another inverse problem, which is the boundary rigidity problem. And of course, it's only, whatever I showed is only in the case of 2 dimensions. In higher dimensions, whether there is a connection, I don't know the answer. Okay, so the determination of G from DG is actually a nonlinear problem, right? Because DG involves square root of Gij, so there is that, it's a distance, right? So it's a nonlinear problem, and as we all know, nonlinear problems are harder than linear problems, right? So let's linearize the problem. So if you linearize the problem, and I'm not going to work out this derivation, it can be done. It has been done several times. So if you linearize the boundary rigidity problem near a known simple metric. So Professor Kim Knudsen did this for the case of the classical Calderon problem, right? So it's a similar calculation here near a known simple Riemannian metric. He did that for the case of constant conductivity, right? So that's how he could use harmonic functions there. So you linearize near a known simple Riemannian metric, then it leads to the following inverse problem. And this is again a very nice problem. So what you have here is the following. So if you linearize it, it leads to the following. So you have the integral of some symmetric 2 tensor field along geodesics connecting boundary points. I assume that this f is 0 outside, so I can go from minus infinity to plus infinity. Don't bother about the limits. But if you linearize the boundary rigidity problem, it leads to the determination of f, a symmetric 2 tensor field. In this case, you can view it as a matrix of functions, but it's not positive, definite, or anything, but it is symmetric. So you have the integral of f along geodesics, and the question is, if I give you G is known, therefore all the geodesics are known. So if I give you the integral of f, which is a symmetric tensor field, which is defined here. So suppose I give you this IGF, does it determine f? And well, that it's not true. We can easily cook up a counter example, and this is motivated by the fact that there is an obstruction to, even in the case of the nonlinear problem, the boundary rigidity problem. So if you try to work that out, this is what it ends up with. So you can take f is equal to dv, where I'm not telling you what this d here is. This d is what we call, see, this f has to be a symmetric tensor field, right? This d is what we call as the symmetrized covariant derivative. So you consider the covariant derivative, but that's not going to be a symmetric tensor field anymore. So you have to symmetrize it. So let's not bother about what the exact definition here is. So you consider the symmetrized covariant derivative of a vector field that is 0 on the boundary. So this comes up from that size chart, where psi is a diffeomorphism such that psi restricted to dm is equal to 0. So there is some differentiation happening. Therefore, along the boundary, it's going to be equal to 0. So if you consider a vector field such that v restricted to dm is equal to 0, then this is just a fundamental theorem of calculus problem. So you can easily see that IGF of this, now it's a symmetric 2 tensor field, along every geodesic is 0. Right? So obviously from this IG you cannot determine F. Again, as we saw in the previous case, the question is this the only obstruction? That's still an open problem. Right. So again, I repeat, you have G to be a C infinity simple Riemannian metric, and you have a symmetric tensor field, and you know the integral of that symmetric tensor field along every geodesic is 0. Does it imply that that symmetric tensor field has to be D of a vector field V which vanishes on the boundary? And it's an open problem, but there are some partial answers. Okay, so symmetric 2 tensor fields are hard, so let's consider a simpler version of it, which is the geodesic ray transform. So what is the geodesic ray transform? The geodesic ray transform is you replace this F here by a function, right? And Professor Jan Bowman, he did radon transforms. The radon transform in 2 dimensions is the X-ray transform. This is the X-ray transform, but the X-ray is replaced by geodesics of that metric in higher dimensions. That's only difference. You can consider the integral of lines in higher dimensions. That's the line transform. We call it as the X-ray transform, motivated by what appears in CT scan, CT imaging. So the generalization of it on a Riemannian metric is the geodesic ray transform, where this F is replaced by a function. Okay, so you consider IGF of gamma along every geodesic gamma connecting boundary points, and I assume if the metric is simple, then the conjecture is so let F be a function, a one form or a higher rank symmetric tensor field. And if you have worked in this field a little bit, usually functions are easier, one forms are slightly easier, 2 forms and higher are really difficult. But the technique that works almost always, that works in 2 dimension, 2 symmetric 2 tensor fields and higher, you can do this for any rank symmetric tensor field. So whatever techniques that work in 2 dimensions for 2 and higher, the techniques are the same, but 1, 0, 1 and 2, there is that gradation, and you will see the results will indicate that. So this is the conjecture. So the conjecture is that if you have F be a function, a one form or a higher rank symmetric tensor field, and if you have IGF of gamma is equal to 0, then does it imply that F is equal to 0 for the case of functions, or F is equal to D of V, where now V is a function on the boundary is equal to 0 for the case of one forms, and for the case of symmetric 2 tensor fields and higher, this D here. So this D for the symmetrized covariant derivative for if F is a one form is the same as the x0 derivative. But if it is 2 and higher, then this D has to be replaced by the symmetrized or the covariant derivative. So the Christoffel symbols come into play. So it's F is equal to dV with V restricted to dm is equal to 0. So this V is either a function or it's a vector field. Okay, and this is a conjecture. But there are some known results. There are some nice known results. So one is that for functions it's true. That is, you consider a C infinity simple Riemannian manifold, and if you have the integral of F is equal to 0 along every geodesic, then F is actually equal to 0. Okay, the answer is also true for one forms, and this was done by Anikonov and Romanov. And for higher rank, it's the conjecture is open. But if you assume that G is a priori simple, of course, if you assume that G is also analytic, then this result is known. And again, it's a unique continuation argument. The result roughly follows in the following way. From IGF, you can determine the Taylor series of F at the boundary, and then you have to be able to uniquely continue inside. Right? Oh, sorry. The Taylor series of F minus dV, where V is equal to 0 at the boundary. There is a natural obstruction. So with that, then you can uniquely continue inside, and that shows that F is equal to dV, where V is equal to 0 on the boundary and V is a vector field. And this is for the case of analytic matrix. Actually, this is not the strongest result. There is an extension. You can perturb this matrix slightly. So in a neighborhood of any analytic metric, a suitable neighborhood, this result is true. But the full conjecture is still open. Okay. Now let me come to what are known as Helgerson support theorems. And the reason why I bring this up is because it has connection to the Calderon problem. So what is the classical Helgerson support theorem? So you consider all hyperplanes. So you take any f to be a compactly supported function, and you consider the integral of f along every hyperplane not intersecting a closed convex set K. So you can assume this closed convex set is a ball, and then you have in the integral of f along every hyperplane. Suppose it's equal to 0, then does it imply that the support of f is contained in K? It's a natural question, right? And Helgerson proved this first. Maybe I'm wrong about that. Let me take that back. There were 2 or 3 almost. So I don't know. So anyway, it's called as Helgerson support theorem. But the proof that I know involves was what I saw in Helgerson's book, and it was proved by Helgerson. So and it is true that the support of f is contained in K. And this was substantially generalized, and a very powerful method was introduced by Professor Bowman and Quinto in 1987. So, and there are a lot of words here, but it's the same analog. Rf of, so you consider a closed convex set K, and then you have the integral of f along every hyperplane not intersecting that closed convex set K to be equal to 0, but they actually have weighted radon transforms, and these are not arbitrary weights. These are positive real analytic weights which are even in omega. And if you have that this R nu, this weighted radon transform, R nu f is equal to 0, then f is actually equal to 0 on, or f is equal to 0 outside of K, or in other words, the support of f is contained in K. And this uses, it's a very nice result, and this uses a very...
So if it touches the K, so all the hyperplanes not intersecting, it could touch or...
If it
touches.
No, there's a closed line. It's close. I'm considering it's close. You take a ball, close ball.
If the hyperplane is touched the as a tangent, then
That's okay. It's to be 0 with a support. So
it's allowing the.
Yeah, that's not a problem. So, so then f is equal to 0 on the union of. So I stated this, although I wrote here, I stated this in terms of the Helgerson support theorem. But one of the crucial theorems that is used here, and which was mentioned by Professor Jan Bowman, is what is known as the theorem of Kawai, Kashiwara, and Harmander. Right? And this uses, so the proof uses analytic microlocal analysis. So what is that? So what is the theorem of Kawai, Kashiwara, and Harmander? So roughly speaking, it's the following. So you have U in D prime. So U is you can assume it's a compactly supported distribution. And roughly speaking, what this theorem says is that if you consider the conormals or the boundary of the support, those conormals are in the analytic wavefront set of F. So this theorem makes this notion precise. So let me not spend too much time on that, but roughly speaking, it's the conormals to the boundary of the support of F belongs to the analytic wavefront set. And this is not true in the case of C infinity. There are zillions of examples, but in the case of analytic, in the analytic category, this is true. And this is what is used. So the notion of eating away at the support of F. This is what is used in the proof of Bowman and Quinto. and to show that the support of F is actually contained in the convex set K. Now, this can be generalized to geodesic ray transforms, and there is a reason why I bring that up, because it has connection to the Calderon problem. Actually, the Helgerson support theorem, the way it is done by Bowman and Quinter using analytic microlocal analysis, also has relevance to Calderon problem. The geodesic ray transform, as it's written here, this also has connections to the Calderon problem. So this can be generalized to the case of the geodesic ray transform, but you have to assume that the metric G is real analytic. Again, because we want to use analytic microlocal analysis. So that way we're able to eat away at the support of F using that argument, using the theorem of Kawai, Kashmir, and Harmonic.
Could I see the previous slide and the slide before that, which was the Bowman's?
Yes.
Okay. So what does this result say? So this is the same as that, except for this weighted case now.
This is the same as this, except for there is a real analytic weight that's even in omega.
Okay. And what was the theorem they used there? The next slide?
So this basically gives you the conormal to the support. That's what that F, the real valued function, describes. So df gives you the normal or the conormal to the support of F. The theorem of Kawai, Kashmir, and Hormander tells you that the conormals, which is df, belong to the analytic wavefront set. Okay, and this theorem is used in this. So this was proved in the case of real analytic metrics, and again, because we want to use analytic microlocal analysis, and actually Stefanov and I, so this is the result in my thesis, and Stefanov and I, we extended this for the case of symmetric two tensor fields. Actually, the same proof also works in symmetric tensor fields of any rank, but the proof here is quite technical. So again, the thing is that you have a closed, now geodesically convex subset, so that replaces the convex subset in the case of Euclidean in the Euclidean geometry, because now you want, if you have any 2 points, the geodesic connecting those 2 points should be inside, right? So that's what you have, the geodesically convex set. And suppose you have that the integral of F, where F is a symmetric two tensor field, suppose that's equal to 0 for all gamma not intersecting K, then F is equal to dV with V on the boundary is equal to 0. And this is the best that you can achieve, because there is any symmetric two tensor field of the form dV, where V is a vector field at 0 on the boundary, lies in the kernel of this geodesic ray transform. It has an infinite dimensional kernel, right? So this is a theorem so this is the case for symmetric. This is true for one forms and two tensor fields and any higher rank symmetric tensor field. Now, what is the connection of geodesic ray transform, or it's the Helgerson support theorem for the classical radon transform or for the weighted radon transform?
Could I just go back to the previous
Yes,
slide?
yes.
I'm still trying to. Okay, so the metric is real analytic, and that's what makes it. Okay.
Exactly. And so there is a connection between whatever was done here to the case of Calderon problem. I will just indicate, but this leads to a natural conjecture. So the conjecture is prove a Helgerson type support theorem for the geodesic ray transform in the C infinity case. Now, this is still, to the best of my knowledge, an open problem, but one has to be very careful. So note that the uniqueness has been settled by Mukhametov. So there was in the previous slide I mentioned that if you take a simple Riemannian metric and then you have the geodesic ray transform of the function f along every geodesic, suppose it is equal to 0, then f is actually equal to 0. It's a proof by it's a proof due to Mukhametov. So uniqueness is settled. So then the natural question is whether one can prove a support theorem, and that is still an open problem. But one has to be careful. This is a very subtle question. There is a very famous counterexample by Professor Jan Böhmen that shows that there is non-uniqueness of the weighted radon transform in the C infinity category. So remember that the Helgerson type support theorem that Böhmen and Quinto showed. Also, in the trivial case that you consider, so you can also show uniqueness, right? Support theorem is a stronger result. So you have uniqueness due to the result of Böhmen and Quinto in the analytic category. You have weighted radon transforms in the analytic category, then you have uniqueness. But in the case of C infinity, there is a famous counterexample due to Jan Böhmen that shows that you cannot have uniqueness. And but I believe this question is still valid because this does not arise as a weighted radon type transform. So anyway,
so just to understand, so the uniqueness question is probably settled from something like geodetically complete null. Whereas if you leave a hole in there,
yeah,
that's the issue with the Helgerson type support thing, right? It's not geodetically complete. Is that what the issue?
It's so far the proofs have involved going from the boundary to the inside.
Right.
So you have to do analytic continuation. So you need a proof that avoids analytic continuation if you want to be able to do it in the C infinity case. So all the proofs so far have gone, from the boundary all the way to the inside. And actually, you will see why this also comes up in the Calderon problem. It's the same idea. Again, this is a subtle question, but I believe that one can prove a support theorem, but it's a conjecture. Okay, so now what is the connection between the support theorem and the Calderon problem? And there is a connection to the geometric Calderon problem. There is also a connection to the classical Calderon problem. And the classical Calderon problem was already mentioned by Professor Rakesh, but I will just repeat it. So in the classical Calderon problem, the Helgerson type support theorem is used to prove uniqueness when you have Nyman data on possibly small subsets of the boundary. Now, why does it appear? So it appears for the following reason. If you have the full data case, then what happens is you end up with the Fourier transform, right? If you recall, even as early as yesterday, Professor Kim Knudsen, so he is trying to recover the Fourier transform with full data. So if you have full data, you recover the Fourier transform. But if you have partial data, and partial data in the sense of measurements on very small subsets of the boundary, then you end up with the radon transform. Or it's a radon type transform, but you end up with a radon transform, and then you want to be able to show uniqueness. And that is where the support theorem comes in. You want to eat away at the support of the conductivity to show that the conductivity is actually equal to 0. And I'm dealing with the scalar case here, not the anisotropic case, but at the scalar case. So this was used in a famous paper by Koenig. Oh, sorry, this case should be capital. So Koenig, Sjöstrand, and Ullmann, and this is a paper that appeared in 2005 in Annals. So where they consider for the partial data case, and one ends up with a radon type transform. Actually, in this particular paper, they work with what is known as the FBI transform, but the proof was simplified later on using radon type transform in a follow-up paper. So the point is, the proof goes as trying to prove a support theorem for the Helgerson type, support theorem for the radon type transform in this particular paper. And where does geodesic ray transform come in? Geodesic ray transform comes in for the geometric Calderon problem, not in the full setup, but for a class of geometric Calderon problems. And there is a recent paper by Koenig and Salo that uses the support theorem for the geodesic ray transform to prove uniqueness. So, and that's the end. Thank you. And I'm happy to answer any questions.